Welcome back, students. In the last video, we did exercise problems in lesson 10, wave optics. And with that, I consider the lesson to be over. There is one part of the lesson which is polarization, which has not been included in this year's syllabus. So I'm not dealing with that, even though it's a very interesting topic. I can probably give you an overview of what it is. Polarizing a light or wave means that making it oscillate in a particular direction. So that is polarization. And this can happen only for transverse waves. Polarization cannot happen for longitudinal waves. How they do it and what are the advantages of this polarization are not going to be dealt with now, because that has been taken out of your syllabus. But I can tell you that the 3D movies you watch, like Avatar and anything else where you have used those 3D goggles, they use this idea of polarization. So without polarization you cannot get 3D. So it has practical uses, but then it has been taken out of your syllabus, so we're not getting into it. So with that, with the last video where I did the exercise problems, I consider the lesson to be over, and we'll move on to the next lesson, which is lesson number 13, nuclei. You have studied about atoms, but now you're going to study about nuclei. Here we'll talk about the mass-energy relationship, the mass defect, nuclear fission, nuclear fusion. Again, at a very general level, because the details of these concepts have been removed from the syllabus. So we'll not be talking about radioactive decay and half-life period and the mean life period, and those ideas we'll not be talking about, but your seniors studied them. But we'll be focusing on what is to be focused on for your final exam, the CBSE exam. So this is also going to be a very short lesson, but this is also a very interesting lesson, and I'll try to give you as much input as possible on the topics that we cover from now on. To talk about this, I have to bring in Einstein. Einstein's mass-energy relationship, the famous E is equal to mc squared equation, that has changed the world in many ways. And that equation helped us build atom bombs. That's a wonderful equation. And it has also helped us build the nuclear reactors that we have around the world. That equation has given us access to a lot of energy with practically no cost, you can say. When I say cost, no cost, nothing is free. When I say no cost, I mean for a certain amount of money that you put in, you're going to get way more energy through the nuclear reaction than in any other way, like using fossil fuels like petrol and building a dam and using hydel energy. Those are all going to cost a lot of money. But a nuclear reactor helps you get energy for a very cheap price. I'm just talking about the production cost of the nuclear energy. But then the nuclear wastes, they put a different demand on the environment and stress and pressure on all of us. And it is always a dangerous game that we are playing. But when the game is played well, harnessing the nuclear energy game, which Einstein's E=mc² equation helps us do, when you are playing this game well, we are able to tap into an energy resource which is very, very, very cheap. But if it backfires, if there is any mishap, then the cost of that mishap would be catastrophic. We will have impacts, damages that will run into millions of years. But while things are going fine, they go fine, and you have access to low-cost energy. We'll study about all that in this lesson, but though not in a very detailed way, we'll be able to get a glimpse of what it all means, how E=mc² can be used to understand a lot of nature. With this introduction, we get into the new lesson. Lesson number 13, Nuclei. You have studied about atoms, and you know that an atom has a nucleus and electrons orbit around that nucleus. And in the nucleus, you have protons and neutrons. Then you assign two numbers to an atom. One is the atomic number, and the other one is a mass number. The atomic number is represented by the symbol or the letter Z. Z is the atomic number. And then A is a mass number. This mass number is not in kilograms or grams. It's just a number. It is not what, if somebody asks like what's the unit of this mass number, we just say there is no unit to it. Why? Because it's a ratio. How can mass be a ratio? Well, it gives you an idea of how many neutrons and protons are present in an atom. Why should you even get to this point? Why can you not mention the mass of an atom in kilograms or grams? And why do you want to say the mass in terms of the sum of the number of protons and then the neutrons? Well, it's because an atom is a very, 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 very light thing. Okay, the mass of a single atom is almost negligible. For example, if I take a carbon atom, it has a certain mass. Usually, each and every element you have in nature will have many isotopes. You have carbon 12 and then you have carbon 14. And if you take gold, there are 32 isotopes of gold, meaning that there are 32 different types of gold. And if you take hydrogen, then you have 3 isotopes of hydrogen. One is hydrogen, the second one would be deuterium, and then the third one is tritium. But then tritium is produced only in the laboratories, it doesn't exist naturally. You have to synthesize, so to speak, the tritium element, which is nothing but hydrogen. So there are things called as isotopes, and there are many isotopes of the same element. And almost every element in nature has its isotopes. So if you take carbon, you have carbon 12 and also carbon 14, and if you take carbon 12, then it has 6 protons and 6 neutrons. So you represent carbon 12 as something like this: C6 12. Generally, an element is represented like this: element X, A, Z, and A. So Z being the atomic number and A being the mass number. So the mass number, if you see, it is simply, in this case, the sum of protons and neutrons. Then that we come back to the same position. Why do you need to mention this number? 6 protons and 6 neutrons. Why? How can mass be a number? Can we not express that in kilograms as we've done for all the other things? In SI units, it's kilograms. In CGS, it's going to be gram. So, why can we not use it? The reason why we would not be using kilograms or even grams for an atom is because, as I said, the atom is very, very, very light. And if you take the carbon 12 atom that we just discussed, the mass of a single atom in kilograms. Okay? So your carbon atom, has its nucleus, and then you have 2 electrons here and then 4 electrons here. So this is carbon atom. And here you have 6 protons and then 6 neutrons inside. This is carbon 12. The mass of this is, so mass of carbon 12 is equal to 1.992647 1.992647 into 10 to the power minus 26 kilograms. Look at this. It's very, 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 very small. So an atom, a single atom, is very light. Its mass is almost negligible for all practical purposes. If you take a single carbon atom, it's almost negligible. So this is not very conducive, this is not very helpful. Using SI units for atomic mass is not very helpful. So you need to come up with some kind of a number, some kind of a mechanism to do this. So the way we do it is this. We take the carbon atom and then we say that one atomic mass unit, simply it's U. One atomic mass unit is equal to the mass of carbon 12 carbon 12 divided by 12. So effectively what you are saying is one atomic mass unit is equal to mass of one proton or neutron. Okay? We still don't know whether they have the same mass. I have not discussed that yet. But you said, you know that there are 12 items in this, and you know that the electronic mass is can be ignored, not much. Okay? So you know, like you take the entire mass of this atom and divide that by 12, then you get one atomic mass unit. So when you do this, you are not ignoring the mass of the electron. Now when you talk about the mass of an atom, it is the mass of the nucleus plus the mass of the electrons. But then the electronic contribution to the total mass is so small that you eventually end up, when you do the rounding off, eventually like you leave at least a part of the electronic mass out. But let's not talk about that. When you say the mass of an atom, it's the mass of both the nucleus and the electrons together. So that's the mass you are thinking. And that mass is divided by 12 will give you one atomic mass unit. So that's for carbon 12. So effectively, since you can ignore the mass of the electrons, one atomic mass unit translates to the mass of one proton or neutron there, assuming that proton and neutron have the same mass, or you can say that it's the average mass of a proton and a neutron. Yes. Okay. So this is what it is. So then what does it equal to? This is going to be equal to 1.992647 into 10 power minus 26 divided by 12 kg. So then 1 unit, that is atomic mass unit, is given by going to be 1.660539 into 10 to the power minus 27 kg. Okay. So this is the atomic mass unit. So many kgs. So from now on, whenever you find this amount of mass, we are going to say that's 1 unit, one atomic mass unit, so which is almost equal to, it translates to the number of protons and neutrons in the atom. So that is why it begins 12 kg. I hope you are able to get this. And if you compare this with the mass of a standalone proton, because the mass of the proton is given to be 1.67262 into 10 power minus 27 kg. You see there is only a slight difference. Very slight difference between one atomic mass unit and the mass of a proton. So you can, for all practical purposes, you can treat these two to be the same. For all practical purposes, one atomic unit is equal to the mass of a proton. And if we see like how many atomic units are there in one proton, notice it, 1.66 is 1.67, so clearly this will have more than one atomic unit, right? Because it's 1.6, it's 1.67. So when you do the calculation, MP by that will give you this mass of the proton is equal to 1.0075 0.27 atomic units. So we take this and multiply by this number, then I get this number. So here the mass of the proton is expressed in terms of kg, but in this case, you see, you don't have the 10 power minus 27 stuff here. It is simply, or is expressed here in terms of the atomic mass unit. So it's almost the same. It's MP, my mass of proton is almost equal to 1 unit. So this for theoretical purposes you get 1.00727 unit. But if you are defining this as 1 atomic mass unit, then you can express everything else in terms of atomic mass unit. For example, what would be the mass of an electron? The mass of an electron is equal to 0.00055. Okay. You see, it's almost 0.0. This is almost 1. Mass of proton is almost 1. Mass of electron is almost 0. Okay, so for all practical purposes, when you do your calculations, we will be taking MP as 1 and the ME as 0 mass. This is how it is, even though they have a mass. So the short point here is that since an atom is a very light thing, it's so small and so light, our conventional units of kg, kilograms and grams do not make sense when you start measuring the mass of an atom, because our units are too big, too big. But we need another unit with which we can measure the mass of the subatomic particles like protons, neutrons and electrons. So we come up with that kind of a unit, and that is what is called as the atomic mass unit, on AMU, and is represented by the letter U. Okay. And how do we define it? Well, we take a standard. Okay. The standard is this. The standard is carbon atom, carbon 12 atom, because carbon has 2 isotopes. So you have to take carbon 12 isotope. So take the carbon 12 atom, weigh the atom, find its mass, and divide that by 12, because there are 12 things that make the nucleus of the carbon atom. So find the mass of the carbon atom and divide that by 12, then you get what is called as 1 atomic mass unit. So this is what we will start using as the unit whenever we talk about the mass of very small things like atoms. And once we know what the unit is, then we are comparing that unit with the mass of a standalone proton and then the mass of an electron. The mass of the proton is almost equal to 1 atomic mass unit, and then the mass of the electron is almost 0. It's not 0 exactly, it's almost 0. You can see that. But actually, in our calculation, we'll still be using these numbers. You can see the rationale for coming up with a new unit to measure the mass of subatomic particles. We have to talk about the discovery of neutron. Neutron was discovered by James Chadwick in 1932. First of all, how do you even know that there is something called a neutron? Well, if you take an element, okay, you know that its chemical properties depend on the number of electrons in the element. We keep saying this, like chemistry is nothing but the dance of electrons. So you give an electron and then you receive an electron and then you form a bond and then you form new compounds, new molecules, like that. So it's basically a dance of electrons. So the chemical property is decided by the number of electrons. The electronic configuration is what decides the chemical property of an element. We also know that an atom is neutral. So if you know the number of electrons, then you also know the number of protons. And if you know the number of protons, then when you calculate the mass of the nucleus with the number of protons alone, then you arrive at a certain mass, certain number. But when you weigh that element, it doesn't match with the calculation, the number that you arrived at through the calculation. You see that there are, say, 12 electrons there. So if there are 12 electrons in an element, which you can decide using the chemical properties of it, and you also figure out that there must be 12 protons because the atom, as you know, has to be neutral. So you also know that the protons are at the center of the atom, and since you know the number of protons, because you know the number of electrons, you know the number of protons, and if you multiply this number with the mass of one proton, then you are supposed to get the mass of the atom. But it turns out that the mass of the atom was much more than that. So that clearly gives you the realization that the nucleus does not just possess protons alone, because if there were only protons, then your mass would be less, but then your mass is more, meaning that there are other things too in the nucleus. So Chadwick was a person, okay, who was able to get these things out, the neutral particles which have mass but they don't have a charge, because if they had charge, then the atom will not remain neutral, right? Because you have 12 electrons, you know. But now here you have more than 12, and the electron cannot, the atom cannot remain neutral. So if the electron has to remain neutral, if the atom has to remain neutral, the number of electrons has to be equal to the number of protons. So the particles which give the extra mass or weight to this atom have to be neutral. They cannot carry charges. And Chadwick was able to get those things out through alpha scattering experiment. So he did that in 1932, and for proving experimentally that these things exist, neutrons exist in an atom, he was awarded the Nobel Prize in 1935. Think about all this. It's a very new. We know about neutrons. We were able to prove the existence of neutrons only in 1932, roughly only 90 years ago. Just in your grandfather's time. Think about it. Okay, so before your grandfather, we didn't have this information. So all this is new. So all these things may feel like they have been in existence forever for you, but that is not true. The existence of electrons was proved only in 1932 with Chadwick. So the information that you get from your textbooks are all pretty new, hardly 100 years old. Anyway, so when we got that out, then we were able to find the mass of the neutron. So the mass of the neutron was is 1.6749 into 10 to the power minus 27 kg, slightly more than the mass of the proton. And if I express the same thing in atomic mass unit, then I'm going to get to 1.00866 units. You remember, the mass of proton was 1.00727 units. And the mass of electron was 0.00055. Okay. A proton, when it comes out of a nucleus, can remain stable. It can remain a proton for a long time. Actually, a proton is nothing but the nucleus of the hydrogen atom. So when you take an element and then you make one proton come out, actually what you have done is that you got the hydrogen nucleus. That's what it is. And then if it captures an electron along the way, then it's going to become a hydrogen atom. Okay. So a proton is very stable when it comes out of the nucleus of an atom. But a neutron is not stable at all. The moment neutron comes out, it becomes unstable. It's very stable inside the nucleus. Inside the nucleus, neutron is very, very, very stable. But then if it comes out of the nucleus, if you take it out of the nucleus, then it starts disintegrating. It starts a decay process. So a neutron is very unstable when it is outside the nucleus. When it is outside the nucleus, it disintegrates or it decays into 3 particles. It destroys itself and then it becomes 3 other particles. They are these. Okay, if you take a neutron out of the nucleus, then it becomes a proton and an electron and an anti-neutrino particle. So it's proton, electron, and antineutrino. These 3 things make a neutron. So when a neutron disintegrates, and these 3 particles come out of it. Okay? So you can see from this you can easily understand why the neutron mass is greater than the proton mass. Because you see this 1.00727, but here 1.00866 is slightly more because neutron contains a proton and then an electron and also antineutrino. So this is very, very, very light particle. Its mass is much less than even the mass of the electron. So it's almost zero. It's very difficult to detect these particles. But understand that a neutron comprises of one of these 3. So if you take a proton and then add an electron and then an antineutrino particle to it, then the whole thing becomes a neutron. Okay, so the mass of a neutron is more than this. So if somebody asks you, where do the neutrons come from, then you can say that it's what you take a proton, add an electron, an antineutrino, then you're going to get a neutron. Or take a neutron, then break it into, allow it to disintegrate, and it disintegrates into a proton, electron, and antineutron. And a neutron does it outside the nucleus in about 1000 seconds. So this is called as a mean life of a neutron outside the nucleus. So if you take the neutron out of the nucleus, it will live there for about 1000 seconds, and at the end of 1000 seconds, approximately, mean life. Some neutrons may take a little longer, some other neutrons may take a little shorter time, but on the average, an average neutron will live outside the nucleus for about 1000 seconds, and when it dies, or I should say decays, then it produces a proton, an electron, and also an antineutrino. So a proton and electron jointly with the antineutrino make a neutron. Hope this is clear to you. So let's talk about the size of the nucleus. So as you know, the nucleus will contain proton and neutrons. They're approximately the same size, approximately, because they have approximately the same mass, so they have approximately the same size. But if you compare the size of the nucleus with the size of the atom, the nucleus is very, very, very small. You may have come across this when you studied about hydrogen. You know that it is, if you take the hydrogen atom, an atom is the outer boundary, right, of the electron. So you have the nucleus, so this is your nucleus, and this is the outermost electronic orbit. So the size of the atom is this. Basically, you say that this is the size of the atom. Or you can also find the radius of the atom and stuff. Okay, so it's the size of the atom. But then when you compare the size of the atom with the size of the nucleus is a very, very, very small thing. The atom itself is very small. The size of the atom itself is very small. Then the size of the nucleus is much, much, much smaller than that. Coming back to the hydrogen atom, you said the size of the hydrogen atom is roughly 10 power minus 10 meters. It's 1 angstrom unit, 10 power minus 10. And then the size of the nucleus, the proton there, is 10 power minus 15. So you say it's almost 1 lakh times less than the size. So 1 lakh times less than the size. What do you even mean by that? How can you make sense of that? For example, if you are sitting in Buxton College, and if I am going to take an atom and then expand it, I expand it in such a way that the nucleus, the proton, the nucleus of the hydrogen atom, okay, it expands to a size of 1 meter. So 1 meter is about the size. Okay. So if I expand this atom and then make the nucleus occupy this size, then the electron that is orbiting around it is going to be in Salem, nearly 100 kilometers from here. So 1 meter, and then there is 100 kilometers from here. So it is that size, and such difference in sizes we're talking about. So from this proton to that electron, the hydrogen atom, there is only empty space. From here till Salem, it's only empty space. So it is, the atom is basically empty, and its mass is in the nucleus. So the entire mass, almost the entire mass of the atom is concentrated in a very, very, very small volume. This is amazing, actually, if you think about it. Okay, so if we just compare the sizes, for example, so the size of the atom is in 10 power minus 10 meters. Okay, something like that. And the size of the nucleus like it's 10 power minus 15 out of 10 power minus 15 meters. Okay, so it is so small. It's 1 lakh and 10,000. I mean, you don't even really get 1 lakh, okay? But somewhere around 50,000, 60,000, that range, because you need to talk about the radius, right? Okay, we'll get aft anyway. So I'll say that then they'll have the order of about 10 power 4. So if you compare the size of the atom with the size of the nucleus, the size of atom would be 10,000, 12, 20,000, 30,000 times more than the size of the nucleus. Okay. So now let's try to make sense of all this. Let's try to estimate the size of a nucleus. Like let's come up with some kind of an equation that helps us do it. For example, let me take one proton. Okay, and then I'll also say that a neutron roughly has the same size. Okay. The proton, neutron, almost same size, let's say. If I assume this, then this radius and this radius, I call this R0, will be the same. So the point here is we'll assume that there is no difference between the sizes of proton and neutron. So I'm going to put these things together and then form a nucleus. And I can have, if I take carbon 12 for example, in carbon 12 I'm going to have 6 protons and then 6 neutrons. I'm putting them all together and then make a big ball. Okay, so I got 12 small balls and I'm making a big ball out of those 12 small balls. Now, what would be the new volume compared to the old volume? So it's very easy to do that. First of all, what is this volume? Protonic volume. The volume of the proton or the neutron is equal to 4 by 3 pi R0 cube. So now I'm going to put them together like this, something like that. Okay. I'm putting them together and then I'm making a big ball. This is going to be my nucleus. Together. So you can understand that the new ball will have the combined volume of all these small balls. If one proton has a certain volume, if we put 10 protons, then if we make a ball out of them, then the new ball will have 10 times the volume of that one proton. Okay. So the new nucleus, I call it as volume V, is equal to the number, I will say, in that case, the number in the nucleus depends on A, right? A is the mass number. It tells you roughly how many are there, how many protons and neutrons are there. So that is A. How many bonds, the small bonds are there, given by the mass number. A into volume of either proton or neutron, roughly the same. So that gets me the new volume is equal to A 4 by 3 A pi R0 cube. Okay. That's the new one. So this is the volume of this ball. So this is VP, and this is V. V is equal to A times VP. If that is the case, then I must have a new radius for this. I'll call this radius as R. Radius of the ball that I created. So that would be, how can I find this radius R? Well, if R is the radius of this volume, then this volume can be written as 4 by 3 pi R cube. That would be the volume of that ball. And that must be equal to 4 by 3 A into pi R0 cube. 4 by 3 we cancel here, pi pi can be cancelled here, and that gives me R cube is equal to A R naught 3. And what is R? R, radius of the nucleus. Radius of the nucleus is given by, we take the cube root, it's going to be R naught, the radius of a proton or a neutron, into A to the power 1 by 3. Okay. So if I know the radius, if you know R naught, then I can find the radius of any nucleus, because the nucleus is going to be made up of protons and neutrons. So if they have the same size, then this equation should work. Okay. So this radius R naught is equal to 1.2 into 10 to the power minus 15. 1.2 into 10 to the power minus 15 meters. So that's what we found, right? So size of the nucleus for hydrogen. Okay, it's 10 to the power minus 15, so that's what you see. 1.2 into 10 to the power minus 15. That's the radius. Okay. So what happens is that I can find the density for this. Correct? So this density, I can find this density. I know the mass. I know the mass of proton or neutron, and then I know the radius of this with 1.2 to the minus 15. So if I calculate the density, so the density is going to be rho is equal to mass of proton or whatever neutron divided by volume of proton. If I do this, then I'm going to get somewhere around 2.3 into 10 power 17. 2.3 into 10 power 17 kilogram per meter cube. So that's the density. It's huge. The density of a proton is huge. And this would be the same density, almost the same density for any nucleus, because you're bringing one of these things together, right? So the volume, the new volume will also have this density. So the density will not change. What I mean by that is, if you take the iron atom and if you also take the helium atom, okay, and if you compare the densities of the nuclei of helium and iron, they will be the same. Or if you take hydrogen nucleus and if you take iron nucleus, if you compare the densities of hydrogen nucleus and the iron nucleus, they will be the same, even though one is a gas and the other one is a solid. The densities of the nuclei of almost all elements will be the same, and that is roughly 2.3 into 10 power 17 kilogram per meter cube. Why this is so? It's because you form all these elements with the same basic thing, which is proton or neutron. They have this density. So when you put them together, the nucleus is going to have the same density. The nucleus of any material you take will be the same, stuff like this. It won't change. But then, why do you have differences? That's because of the size. Even though if you take an atom, the whole mass is concentrated at the nucleus. If you take the atom, the size of the atom, that also includes the electrons. So this is the size. And the electrons don't give you any more mass than this, right? So the mass of the electrons in an atom is negligible. So almost all the mass is coming from the nucleus. But now, this is not the volume. The nuclear volume is not what we're talking about. Now we're talking about the volume of the atom. So this mass is now distributed over this volume, because the next atom is going to be somewhere there. So you have this nucleus, and this would be the size of this atom, and that would be the size of this atom. You see, now the masses are distributed over a longer volume. You can see that, right? Here is one, here is the other one, third one, fourth one, fifth one. Now you take a certain volume, a considerable volume of matter, then the nuclei are distributed very sparsely, because most of it is empty space and there are electrons. So the size of the atom finally decides the density of the material, okay? Not the size of the nucleus. The nuclei, all the nuclei will have the same density, almost the same density, but not all materials have the same density. The material density will be different because the nuclei are distributed over longer volume, over a bigger volume. So same mass, now you have bigger volume, so if you consider density, it's going to be less. For example, if you take water has 1000 kilogram per meter cube. Compare that with water. So density of water is equal to 1000 kilogram per meter cube. What is that? That's simply 10 power 3 kilogram per meter cube. So this is the density of water. Compare that with this. It's 10 power 17, 10 power 3 and 10 power 17. The density of nucleus is way more than this, incredibly more than this. And then the size of the atom, and then the fact that atom is mostly empty space brings down this nuclear density to this molecular density, so small. Hope you understand this.